Welcome to the AI show. I'm Scott Stevenson, co-founder of Deepgram and all-around great guy. With me is Jeff Ward, aka Susan. He's a Navy pilot, acclaimed dad joke writer, and AI scientist at Deepgram.
Hi all.
On the AI show, we talk about all things AI. What is it? What can you do with it? How does it affect you? And where is it going? And we ask big questions. The big question today is, what are the dinosaurs of ML? Machine learning, if you don't know what ML is, machine learning. What are the dinosaurs of ML?
Well, actually, I have to do this one. Why can't T-Rex clap?
I don't know. Why?
Well, come on, take a guess.
It's got little arms.
No, because he's dead.
Really?
Yeah.
Really?
I had to pull out a dinosaur joke since
Really?
that's the show today.
Really?
Really?
Yeah, that's it. You want to debut your dad joke as that one? Okay.
All right. No, so yeah, the dinosaurs of ML. This is such a rapidly changing field, and it's taken over quite a few places. So it's a great thing to kind of review some of the things that have changed over time.
Yeah.
And look at them. And there's some great industries out there that we take for granted now how much better they've gotten, or in some ways how much more they can squeeze money out of you, just as the technology's evolved and made
The
things
world
better.
Gets more efficient.
Yeah, more efficient at taking money out of your wallet.
Getting you to click on the best ads.
Exactly.
Yeah.
But
yeah, you can look back at computational machines, right? And maybe start some history back in the 1800s or something like that, right? But electrical, like real sort of automated stuff only started to come around in like the mid 20th century, right?
Yeah.
It's like 1950s, 1940s, something like that.
Yeah, I mean, before that, people obviously
They calculated stuff.
Yeah, they did curve fitting. People have always been intelligent. There's, I'm guilty of this myself. Everybody's guilty of this. It's
Being intelligent?
There's those people in the past. They just didn't know, and it's like, yeah, you just happen to have programs sitting around that do all these amazing things automatically that would have taken them weeks to do. They weren't dumb. They just didn't have the tools you've got.
Yeah, it took time when you have to write everything out by hand.
Yeah, and then we start getting things in the 50s that can start doing these calculations and doing amazing stuff. And then the 60s and 70s. And by the time you hit the 80s, man, you're really starting to get some real stuff there.
Yep. Yeah, so real electronic computation comes around, and it's starting to be used like a lot of things when it's first used, like for defense, fighting wars, things like that, calculating the trajectories of your artillery. But then it starts to branch out after that.
Yeah, and machine learning, from the dinosaurs perspective, actually one of my favorite dinosaurs to go over, and I think we've mentioned once or twice before, is translation, right? Because this has always been a hugely important thing, and of course the roots of it, initial funding of it, comes from military trying to get those Soviet documents turned over to English so that we can read them and figure out what's going on, or stuff like that. And so early work in like the 60s was being done with computational translation, and it wasn't very good, right? Like the initial techniques just weren't quite there. But as we got to the 80s, we started finally seeing the first glimmer of hope, with a whole bunch of great work coming out of IBM, and really putting down the basic components, not necessarily the best answers to them, because they were developing them, but putting down the basic components of modern translation, and defining the problems. How do I align these words? What
do you mean by aligning?
Oh, well, you say something in language X, and grammatically you may put this before that, right? Well,
yeah, there might be a different ordering, or there might be new words added in.
Yep. Right. So they had to define this concept of just alignment here. Like, if I'm translating this little chunk of the sentence, where does it need to go in the final finished product? And just knowing that's a problem and defining the kind of the boundaries of it helps you attack it and get better and better and better at it. And then there's just a bunch of other problems. Is there really a one-to-one word translation, or do you need more words in one sentence than the other? And they started attacking these one by one, and came up with their models of translation in the 80s. which were pretty groundbreaking and started actually doing for the first time. Still not good, but something that people could see the hope on with translation. And then, of course, along comes now.
Mm-hmm.
And we've taken those concepts and we've taken those individual pieces and we've put really heavy machine learning, deep neural networks, recurrent neural networks in place. And we have been able to take their basic concepts and put, really good working, algorithms behind them. And you go on Google now and you've got translations that are quite good.
Mm-hmm.
You read that stuff and you're like, yeah, I can read that. It's like,
it wasn't too long ago where Google was doing translations or Facebook was doing translations and people would laugh at them and be like, this is hilariously bad.
Yeah. But now you're like, ooh, scary.
Yeah, that worked.
Yeah.
That was cool.
And that is evolving so quickly. Even just to, so what, about 3 years ago, 2 years ago, something like that, Google started rolling out worldwide their newest, translation. I believe that's roughly the time frame. And that was all, deep learning and using a thing called sequence to sequence with attention. But this new way of doing things just took over, and you started saying, "Oh wow, it's good." And I can guarantee you that they have vastly improved on that whole thing since then. I mean, this is just such a huge deal for them. Right?
Well, sure, yeah. There's a difference between what you do in research and what you've rolled out for production as well. And your research stuff is generally better than what you've rolled out for production.
Yeah.
Just always. So
yeah, it's the cool stuff.
Yeah.
But I mean, translation's great. What other areas have you been thinking about there, Scott?
Well, I mean, there's I'd like to think of the world as images and audio and text, and you just hit on translation text. Another thing that happens in text is just trying to predict like what is going to happen next. Hey, all these words happened before. What's the most likely word that's going to happen next? So those are language models. Those used to be n-gram type models with a back off model that was a very statistics based rather than a real learning model. And that was just very, very recently that switched over to being deep learning based, like meaning 3 years ago, people are using n-gram models and specifically for a component in speech recognition, but also in other areas of text. And so I think that one has been even more recent than like the translation, and if you go back for images, it was around 2012 where things started to shift there too, where people had different versions of image detection where they would code their own like eye detector or code their own nose detector and try to stretch and scale things and look from different angles and try and figure out what does somebody's face look like from different angles and what would their nose look like and try and put all those different transformations in there, do it all by hand and be like, wow, look at how good it is. It's 70% accurate, and then deep learning models come around and slaughter it, it's like 84% accuracy now. And then a couple of years later, it's 90% accuracy. And a couple of years later, it's 95% accuracy. It's like, whoa, those are just ancient now.
Oh, yeah.
It was 7 years ago.
Yeah. I mean, in internet years, it's even more than dog years. It's
yeah.
like, 50 years ago, right?
Yeah, it's forever ago. But that was cutting edge stuff,
Yeah.
and people, this is stuff that had been worked on for decades that represented thousands and thousands, hundreds of thousands of man hours where academics were getting their grant money together and getting their data sets together and putting it all together and having their grad students, burn the midnight oil, figuring out all these different things. And they start out in the beginning, like early, 80s or early 90s or whatever, like really heuristic-y, and then they start to figure out like, hey, maybe we should throw some stats in here and then we should figure that out. Then you kind of get it all working together. You steal some things from the text area, you steal some things from the image area, you start to get those all together. But then everybody gets blindsided, in the like mid 2000 teens there, right? And deep learning is here, and all those people that used to be working on that stuff aren't working on that stuff anymore. They're working on deep learning now. And I think that's what we really mean by the dinosaurs, like an asteroid came and dropped on the earth and just obliterated, and everybody's doing deep learning now.
what used to be 90% of the academia focused here is now 0%.
Yeah, yeah, exactly.
And that the person that remembers back in the day, just a couple years ago, it's like, remember when we were doing? Oh man.
Yeah.
But no, image is great. You follow the ImageNet challenge, right? Like you're looking at the evolution of the algorithms or the models that go in there. It's just you really see how quickly the dinosaurs get slaughtered there, right? Like, I mean, you talk about again, I'm gonna have the dates here wrong, but some of the earlier models for the challenge were just deep, up to like 20 layers, lots of convolutions.
Yeah.
And that did great.
Yeah, that'd be 2012 to 2015 or something like that.
Right. But then along comes the dinosaur. So they went from the sequential, just layer to layer to layer model. And the problem with that is signal, right? It's like the telephone game. The more layers you have, the harder it is to actually back propagate, train these things, right? And you have to do all these tricks to get them to that point. And so the next thing to try to fix that is a thing called a ResNet, and that's
So in these models, you have like an input image, but then it's layer, lots of layers. And then at the bottom is where you actually make your prediction. I think it's a human face, or I think it's a dog, or I think it's something like that. But that's also where you make your errors. Maybe you made a mistake there, right? Okay. Well, the way that the training a deep learning model works is, hey, I made a mistake there. Now I need to go backwards from that one step and try to update that layer. And then from that layer, I need to go backward and update that layer and keep moving backward. And so what you're talking about is the vanishing signal going backward. Yeah. It's you have your error here, but as you're going backward, the error either tends to blow up and obliterate your network, or it tends to die off and you can't train very deeply, basically.
Yeah. And so the solution to that is effectively make it look like you're all at the last bit right there.
So take the information that's at the top and transport it down to the bottom, allow them to be connected in that way. So now it's less of this one-dimensional flow.
Yep. And that made a staggering difference. They were able to go from depths of, up to 20 to now depths of 1,000 and still be able to train.
Yep.
And that just means those more parameters allow you to, learn more interesting details along the way.
Yeah, and this is where if you follow that, you see like Google's Inception framework or model modules essentially that like determine whether they should turn themselves on or off, but they're just like this. They're a network inside a network and just massively connected. And then if you sort of stack those all together, they would achieve really good results, but it would be like 200 layers or something. It's a lot. And some of them might be turned on for their convolutional side or their standard just dense transformation or whatever, but that's just how it's all constructed. But if you trace the signal going through, it would be going through many steps.
Yeah. So, and actually, with that, there's been a real push to make these things smaller, make these things faster, for a lot of reasons. That makes
it's
it
a good point,
right?
It's a good point. It takes a lot of computational power to train those. It takes a lot of memory to hold everything that's there.
Exactly. And then if you actually want to use it in something like a self-driving car or something like that, that just becomes not practical. You may be processing, I don't know how many image signals coming into that vehicle, and each one of them has to do that in real time.
You got 10 cameras.
Yeah.
And even if you downsample and it's only like 100 pixels by 100 pixels or 400 by 400, you still are doing a lot of number crunching.
Yeah, you're doing a lot of number crunching. But yeah, so that the dinosaurs that we're originally talking about there is just how the idea of this simple, step to step sequential model has just been kind of crushed, because depth does matter, and finding those ways of getting past that has really made huge strides in and the tasks that we're out there with. I mean, ImageNet is just such a fun thing to play with if you can figure out how to grab all that data and train off of it and get the whole kind of construct working. there's a lot of cool stuff that you can learn by playing around with that.
Yeah, there's an ImageNet competition, but there's also a data set that
Yes.
people call ImageNet, and that data set is very large, and you can just go grab stuff from it. And there are models that are already trained. You can go download them from Google or other people and do transfer learning and figure out what kind of handbag something is if you have that data set. And you train your own model to do that.
It's a really popular stepping off point for commercial products that are going
Yep.
to do their own special thing afterwards. You train on this generic large scale thing that really gets your model started.
It makes your model go to college, basically.
Exactly.
You send your model off to college, it learns about all these different things, right? But it's not specialized in life yet. And then it goes and gets a real job and learns on the job, and then gets really good at that job and specializes.
Do you ever think it misses all the puppies and kittens it was looking at before?
I think it misses the parties from back in those days.
Oh yeah, you
Yeah.
know. But what an image party? It's got oh man.
There's a lot of hallucinating going on.
There's probably a lot of flashing too.
Yeah. It's yeah.
Images going to town.
Yep.
Now, really awesome stuff there. Another great area that there's a lot of dinosaurs where the technology has changed to almost unrecognizable but you can still see the roots there. Is pricing.
Mm-hmm.
I mean, Amazon does a tremendous amount.
Tell me about pricing, Susan.
Pricing. How does pricing work?
Yeah.
Basic.
What do you mean by pricing? Pricing what?
Yeah.
There's a marketplace?
Yeah.
What marketplace for what?
Everything.
So like I'm back in the 60s and I got my cell phone and I'm like, where am I going to get a ride?
Yeah.
No. So, but what would be happening then? Like in the 70s, 80s, something like that.
Yeah. So
what's the cool new stuff? Like airlines?
Yeah. Airlines. I hear airlines did a whole lot of great math back then.
Hey, you want to buy an airline ticket?
Yeah.
Yeah, no problem.
And let's figure out exactly how to juice the most out of a person.
Yep.
By varying prices over time and figuring out when they're at their most vulnerable. The point at which they're willing to cry and just hand over their wallet.
Yeah.
It
was one of the first times where you could have a price set and somebody would buy that ticket, but it could be adjusted on the fly, essentially. And it could be adjusted on the fly in many different areas because communication could actually happen, right? And this is very different than if you go into a normal store and you're like, hey, I want to buy this bar of soap. What are they going to do? Well, they could do this,
Now.
They could put like a little digital price placard there, and they could change the price on it as you're walking around. They could have cameras size you up and be like, "Oh, this guy will pay more," Or in our case, like, there's no way these people are paying a lot.
Do like an overlay, augmented reality on your phone, so you get a personal price just by holding your phone up and it says, "Oh, the price for you."
Yeah, but they're following you around, and if you're a big spender, then you get all the customer service. Well, but as you know, if you walk into a normal store, if you're going to Target or Walmart or whatever, this isn't the experience, right?
No.
It's just you got prices stuck on stuff. You walk around, it's just a flat thing for everybody, whoever walks in, and that's what you get. But if you are calling in and buying an airline ticket or going up and talking to the person at the desk and buying it, fine. But now you're buying it online, and basically everybody buys everything online now, right?
Pretty
so
much.
the prices, now they can change every time you load the page, or even while you're sitting there. Yeah.
It's like, but I just clicked on it was $372, but why is it now $648?
Yeah.
As soon as I get to checkout. They've realized that they
you can shift things around.
No problem.
Yeah.
That's and those have really gotten a boost. Like those original algorithms, right? They were computer driven, but they had to estimate things with simple statistics.
Well, they didn't have the computing power either to do like a whole bunch all at once, right? Yeah.
But now we can get much better estimates of those basic underlying things with deep learning technologies, right? So the original algorithms are sort of still there. The ideas behind the algorithms, some of the big ideas, just like in translation.
Oh, sure.
But just like in translation, those estimates have been now backed by really good deep learning algorithms And
yeah, there's some things that survive the test of time,
Yeah.
essentially, like how you would price. But now you're using better models to base off that underlying principle. The same thing with translation. You're using better models that are based off that fundamental principle. But like for image recognition, not so.
Yeah, not so. No.
Some things not so. Yeah.
No, a couple things from like the feature world kind of trickled over, but pretty much everything else.
Yeah,
thrown out.
speech recognition is similar too. It's
Yeah.
like time is going on, and that's similar. There's a wave. There's an audio wave that is being ingested. That's similar, but nothing else is
Yeah,
similar
I mean,
anymore.
you look going on to the speech world, like some of the original attempts were just they had big graphs. Literally, this word can lead to those words.
Yeah.
And nothing else.
Yeah. From this word, it can go to those 4 words.
It was like this big, huge flow chart of all the conversations that could ever possibly happen in the English language. And it's like, you are right here.
Yep. Yep.
And that's it. And that allowed them to be very focused on the speech side of the house. And, it gave them initial, I guess, results if you were very constrained in what you said and how you said it. But it's absolutely nothing like what we do now. I mean, there's some ideas there of like a language model there, but it's definitely not we're not using a big graph to say what's going to be said.
Like the simplest thing you might try to do is take like the waveform of 10 different people saying a word and then just like take the average of it or something, right? And then it would be like this weird average, or maybe you don't just do the wave, you do some kind of Fourier transform to turn it into a spectrogram so you can look at frequency versus time or something like that. But now just take the average of that and say like, okay, now I'm going to compare against that average. Actually, that would work to some degree, given the same type of microphone, the same type of environment, and the same type of people who are saying it, then it'll work pretty well, right? But when you want it to generalize to other things, like it just that's not going to work, which is very similar to the image world where it's like I'm going to make a nose detector and I'm going to try to figure it out from all these different angles. Well, hey, there's a lot of things that you want to recognize in the world. You want to recognize wheels on cars and wings on planes and rivets and stuff like that. And are you going to go and make like a rivet detector and go down that route, or are you going to come up with something that can actually build itself? And that's really how deep learning image recognition works.
Yep. And on the speech side as well. You know, it's like trying to code in very specific stuff might get you that very narrow area a little bit better, but you're probably going to be hurting yourself in the long run because, like you said, you got to be general. Yeah,
and if you've ever used Dragon from back in the day, like 90s.
I had that on my 46.
You get the headset. You're like, this is so awesome. It's a box software, right?
Yeah.
Pop it in, install it, and then it says you can train a model.
Yeah.
Right? Yes, I'm gonna train a model. I'm gonna sit down. I'm gonna read all these, like the quick brown fox jumped over the brown dog or whatever it is.
I remember doing that.
I'm just gonna cruise through them, and then you're gonna try your transcription hand and like go for it. And you're like, wow, it still doesn't work all that well. I guess I have to train it more. The problem's me.
The problem was me. I had that exact same experience. I forgot how long the training took. But
half hour,
something like that.
Yeah.
Sit down there, and at the end of it, I'm just trying to get it to recognize yes and no.
Yeah, exactly.
And it's like yes, no, and it's like not coming out.
Yeah.
It's like.
You start out with these huge dreams, and then you're like, anything, please.
It's going to be so cool. I'll be able to have like macros on my computer. I can map what I say.
Yeah.
It'll be like in the movies.
Write an email. Yeah. Everything is brought up for you. Yeah. Well, that's not laughable now.
No,
which
it's
is
really not laughable now. In fact, it's not only possible, it's happening.
Yeah,
right?
but it's because of that difference. You used to do this comparison of like, well, here's kind of like what the average looks like, and here's what that looks like, and you try to do it, but people speak with different tones. They could say like yes, or they could say yes, or they could say yeah, yes, or whatever, right? And so they could say it very slowly, yes, or yes, or very quick, and so all these things are just hard to keep track of.
But it's not to say again that these things were bad trials or anything.
No, they're
these
great
were
steps.
Necessary. And they were genius for the things that they did.
Yep.
Right. You look back and you say, if I knew nothing and there was no supporting. There wasn't Wikipedia, there wasn't Stack Overflow, there wasn't Google.
Do you remember that? Books, reading programming books.
I know.
Yeah,
you've got to go through all the challenges of just coding something in the first place back in the day, and then coming up with all the technological ideas about how are we going to try to recognize speech and how are we going to recognize images and all that. And trying 50,000 things and finding out that 49,998 of them don't work very well. Those last two, man. And then from there, you go on to the next one, and for the next one.
Yep.
And eventually, you get to the modern world, and it's pretty amazing what those initial things did. And what's really amazing is to see the pieces that survive from those. Those are, like you mentioned before, those really durable ideas are golden.
Well, you could speak to the translation side a little bit more. I don't know quite as much about it, but what are the fundamental laws there?
Oh, well, so there's sort of like a fundamental law of not speech, but of language, not a fundamental law, but a fundamental equation of language. And if you look at it, it's really kind of like Bayes, if you're it's
like Bayes' theorem.
But you basically have this, imagine, if you will, you have the universe of all possible sentences in a language, right? So every single language that could possibly be out there, English, or French or whatever that you're trying to get to. And so given that there's this huge, set of all possible, sentences, what's the probability of each one of those? If you could have this perfect little lookup table, this sentence, eggs danced randomly, is probably less probable of coming out of somewhere than I'd like to go to the store, right? So there's this one fundamental concept that coming out there that is half of this equation, which is the language model side of the house, right? Like the probability that the translation you came up with is actually a valid, good sentence in the language you're going to, right? And then you've got the probability of an individual translation of the original sentence. So, just given this, without an understanding of the language I'm kind of targeting it at, what would I translate this word to, and this string of words into, right? So this combination of the probability of that with as a translation and the probability of the translation as an actual valid sentence, combining those two pieces together gives you a way of judging all these different translations that you could have come up with, and picking the highest one. It now becomes your translation.
Yes. So maybe like you're going from one language to another, and the naive approach is you could take every single word that you see in that language and then translate that individual word, right? And then now you could just randomly order all of those words. If this is one way that you could do it, just randomly order all the words. But then if you have a language model that tells you from beginning to end, if it's in this sequence of words, then this is the likelihood of that being a real sentence. And then you just jumble them all around, and then pretty soon you have like a top 5 that actually make a lot of sense, right?
And not only do they make sense as a sentence in that language, but they make sense as a translation of the original one, right?
Yep, in both ways.
And that fundamental idea of those two pieces you find in a lot of speech and related stuff. You see that in a lot of speech models for transcription, and you see that in translation. These two halves, and a lot of that came out of, like I said, the 80s, the work, back then. So that golden idea,
like IBM,
the IBM models. If you want to get a really good, history view of translation, go to IBM Model 1 through 6, I think it is. And those came out, like I said, in the 80s, and groundbreaking ideas. Every single one of them explored some new piece to bolt on to the idea of how to translate. And each one of those, those ideas have carried forward, right? The problems that they were trying to attack carried forward. Sure, we've solved them in some interesting new ways since then, but man, it's just brilliant stuff to read through that.
Well, interesting things have happened to the people that did that too.
Oh yeah, they're rich now.
Yeah, they a lot of them just left and said like, I'm done with this. I'm going to go to the finance world and start a hedge fund.
Yeah, and then now they're billionaires that probably control the world.
Yeah.
Because what is it to model finances, right? It's this
It's a sequence.
Right?
Yep.
Their whole task there was figuring out the sequence, right, and finding tools of attacking a sequence.
Yep.
And an unbounded sequence, and that's what we deal with all the time in speech. So. Like you said, the big one, predicting the next word. Well, what if it's not? What if your vocabulary isn't English words, but your vocabulary is up or down?
Yep. Buy or sell.
Yeah, buy or sell. Up by 5%, down by 5%. And predicting the next word there equals real big money, right? So the same tools that they developed to deal with these sequences and come up with how to deal with probabilities and stuff of that nature, turned into how to make a ton of money.
Well, they shaped our world now.
Yeah.
Yeah.
I mean,
shaped the finance world at least.
Truly. Yeah.
Yep.
I'd love to see what their secret algorithms are and set, because they're pretty. Who's gonna give out the algorithms that they actually use to figure this stuff out anymore?
They probably don't even know what they're using anymore. They've gone through like 15 iterations of different quants that they've hired.
Yeah,
right?
Exactly.
Yeah. It's like don't touch the system; it's working. Yeah.
Well, again, that's another dinosaur. Like when you look at trading, algorithmic trading has taken over. We had the flash crash. We've had these different things due to algorithms. But I've heard stories tell that. The buildings closest to Wall Street are all filled with computers.
Yep.
Just so they can cut the transmission
Absolutely.
time down. Like building fiber optic lines that only carry one thing, buy and sell orders, for miles away.
Well, fiber optics is compared to the speed of light, still only 2/3 of the speed of light. So what a lot of people use is microwaves.
Yeah, that's right. There we go.
Yeah, get that little edge.
Just that little. Come on. If we can get really, really good at gravitational wave detection, you can just send it through gravitational waves, right?
Yep.
Maybe do neutrinos. That'd be more practical.
Well, I'm pretty pumped about the dinosaurs that are being created now, which is this is the first age of new type AI, like fully learning, very data driven, completely data driven, and it takes a lot of esoteric stuff to put together and just you're putting together like old computer stuff, like just trying to get it all together, but just to get the first version around, get the first thing working. Those will be dinosaurs in 5 years now too. Totally. It'll be like, haha, look at how we were training back then. It was so cute, And now we have silicon photonics, and that's how we train our AI chip, on our AI chip with our petabytes of data running through it.
Yeah,
wasn't that so quaint back in 2019?
Yeah, you remember when we had to think about batch sizes?
Yeah, exactly. Yep, memory was scarce. Yeah.
All these quaint little things.
Yep.
I could just imagine taking your entire training set and actually doing it as a single batch. Oh, man.
Well, that's what people used to do. That's why it's called a mini batch now. Yeah. So, yeah.
Just do that with a few terabytes now.
Yeah, try that. Yep. Okay. Well, thanks for joining us on the AI show. What questions do you have about AI? Comment on YouTube or Twitch, or tweet us at Deepgram AI. We're Scott and Susan from Deepgram. We come in peace.
We're not robots.
Certainly not. We'll see you next time. We were like this.
I think we were.